Hi everyone, my name is Nakul, and I'm here today to tell you a story. The story is called The Perpetual Fragility of Creeping Hillslopes. This is a story about a sand pile. You can see a sand pile being poured here as grains rain from the top, the free surface avalanches, and we can see what looks kind of like a fluid. But this sand pile is more than just a pile of sand. It's a tool for understanding the physics of how soil moves on hillslopes in nature. The world around us isn't as solid as we think it is. This is an example of a landslide in Brazil. Portions of this landslide appear solid, but at other times it feels like a liquid. You can see here that the soil almost looks like waves bashing against a pier. Landslides like this aren't unique. They happen all around the world to great cost for both human life and to infrastructure. It's pretty obvious when landslides happen in landscapes. They leave telltale scars, and we can tell where flow has happened. But there are many landscapes where there are no evidence of landsliding at all. And geologists for a long time have intuited that there is a flow called creep that happens on landscapes like this over millennia. But the exact mechanisms of creep are unknown, it's ambiguous, and it hasn't been ever observed directly. So I'm going to ask a simple question. What is the minimum number of ingredients that you need to manifest flow? And to do that, I'm going to conduct an experiment. The experiment is pretty simple. I just pour a pile of sand on a table. The pile is enclosed between two plexiglass boxes. We illuminate the system with a laser. We want to be very, very sensitive to the motions that we can measure. So this laser generates a speckle pattern, and this speckle pattern allows us to access very, very tiny grain motions. To give you an idea of the magnitude of these grain motions, think a billionth of a meter. This is a fraction of the width of hair in your head. And this is an example. On the top right here, you see grains being poured into the system. The grains are illuminated by LED light. And beneath here, you can see the texture of the speckle pattern and the pile being formed by a series of successive avalanches. Once the grains are done being poured, this is when we begin to observe. I should mention that the system is sitting on a vibration isolating table in a basement across the street. This is about as quiet of an environment as we can get. And once the final grain is done being poured into the system, this looks like nothing is happening, right? But in fact, the sand pile is moving. It's alive and seizing with motion in a picture that's just as dynamic as the landslide video that I showed you before. There are little popcorns of deformation that blimp in and out of existence amidst a sea of motion. So this may disturb you, certainly disturbs me. A pile of sand just sitting on a table doing something that nobody would expect. And a natural question that you could ask is, okay, does this go on forever? I don't have an answer for that. That's a mystery. But go on a little diversion with me, a little side quest, and consider the darkness of space, okay? Space is even more quiet of an environment than the basement across the street. And in space, there are comets and meteors that are basically big piles of sand. This is a picture from a meteor. And what we can see is around the corner here, there's sun peeking around here. And that sun tells us something pretty important, but pretty simple. And is that heat is the most ubiquitous form of mechanical disturbance in the universe. You can't escape heat, right? And this inspires us to ask the question, well, what if we tickle our sand pile a little bit with some heat? And to do that, we introduce a sinusoidal signal. This is a modest temperature change, up and down with time. And the sand pile responds by breathing in lockstep with the temperature cycles. So, what does this tell us? It tells us that the answer to the question, does creep go on forever, is kind of a moot point. Because even in the deep recesses of space, there's heat, which allows creep to continue. The second thing that it tells us is that the sand pile is exquisitely sensitive to mechanical disturbances. In this way, it is fragile. This fragility now, combined with this view of creep, allows us to reconsider disturbances in nature that lead to landslides. So consider the small earthquake that does not lead to a landslide or a very tiny rainfall. With this new view of creep, there is an entire region beneath our perception where weak disturbances and creep play with each other. And there is a hint that the interaction between creep and weak mechanical disturbances hold the key for predicting when and where failures like this will happen. So if I leave you with anything today, I hope you look at the world around you with new eyes, and you consider even the most humble patch of dirt as not something that is static, but rather that is something that is alive and beautiful. And when you look at a hill or you're contemplating a gentle landscape, there's beautiful creep that is happening beneath our perception. If you'd like to know more, you can check out this paper. It is entitled the same thing as the talk, Perpetual Fragility of Creeping Hillslopes. And also you can read this paper by Adam Mann, this piece by Adam Mann, which gives you a sense of the larger scientific context of this work. Thanks for your attention.